One of the biggest hopes for the James Webb Space Telescope, JWST, is whether it can tell us whether the TRAPPIST-1 system planets are habitable or not. TRAPPIST-1 is a system of 7 exoplanets orbiting around a red dwarf star much smaller and cooler than the Sun. Now, all 7 planets are around about the same mass and size as like Earth, Venus and Mars in the solar system. So they're thought to be rocky, but they orbit much closer into their star than the planets in the solar system do, well within the distance from Mercury to the Sun. But because the TRAPPIST-1 star is so much cooler and smaller than the Sun, it gives out less light. So the amount of light these planets receive still puts a few of them in the Goldilocks zone around their star, where it wouldn't be too hot or too cold for life to exist. On top of that, the star and this whole system is estimated to be 7.6 billion years old. That's 3 billion years older than the Sun and the solar system. So there has been plenty of time for life to develop on these planets if they're habitable, if they have atmospheres. And that is the big question here that we're hoping that the James Webb Space Telescope, JWST, can help us answer. The problem is, there's been a lot of chat recently in the community about whether it's even worthwhile us looking for habitable planets around red dwarf stars, because you've got those planets so close into their star, which means they're going to be bombarded by a huge amount of radiation from those stars, especially when the stars are incredibly young, giving out a lot of X-ray and UV radiation as well, which essentially, as it bombards those planets, strips their atmospheres away and possibly leaves them inhospitable to life. But this month, this new paper by Krissansen-Totton and collaborators was published, which says that not all hope is lost, and that TRAPPIST-1e, one of the planets that's in the habitable zone, according to their models, should still have an atmosphere and be habitable. So there's a lot of background info that we're going to need to cover in this video to give you all the context for understanding this really cool result. So first, we're going to chat about what's been found about TRAPPIST-1 so far with the Hubble Space Telescope and JWST. Then what we think is happening with planet formation around red dwarf stars just in general. Third, what this new model from Krissansen-Totton and collaborators is showing for the planets TRAPPIST-1b and 1e. And then lastly, when will we finally get JWST results for TRAPPIST-1e? And just to say, given how high everybody's expectations are about JWST possibly finding a planet that is habitable and hospitable to life, if you see anybody on the internet reporting on something like this, including myself, you should always double check with official sources for any news. Like, for example, the NASA JWST blog. That's a great place to start if you want a more in-depth dive into any recently announced research. Now, websites like this are all written in HTML and JavaScript coding languages, which can help make a website look really professional and stand out, which is really important if you want to put together a website for yourself or maybe even your own business. But if you don't know how to code, then that's a really big barrier to creating a website. That's where Squarespace comes in, the sponsor of this week's video. With Squarespace, you can boost your brand and engage your audience by creating a beautiful, professional-looking website that is easy to use. Their all-in-one tools help you find a template that fits your vision, and it's all just simple like drag and drop coding, so no coding skills are required. They've developed design intelligence, combining 2 decades of industry-leading design expertise with cutting-edge AI technology to help you make a beautiful, more personalized website. Squarespace just makes all the difficult things about having a website and an online presence just really easy. Their built-in store feature lets you quickly and easily sell products, content, or even your time, whatever it is that your business needs. Having all of that in one single tool for all your website needs is just a no-brainer. So go to squarespace.com for a free trial, and when you're ready to launch the website you've created, head to squarespace.com/Dr. Becky to save 10% off your first purchase of a website or a domain. So thank you to Squarespace again for sponsoring this video, and now let's dive into what we know so far, thanks to the Hubble Space Telescope and the James Webb Space Telescope, about the TRAPPIST-1 system, at least in terms of habitability. Well, for context, the 7 planets in the TRAPPIST-1 system were actually only confirmed back in 2017 after a dedicated observing campaign by Gillen and collaborators since 2015. And then, just so there's no confusion about names and terminology, right, all exoplanets are named first of all after their star, so in this case TRAPPIST-1, and that's like TRAPPIST-1a, the thing in the system, and then the planets are named B, C, D, E, F, G, etc, etc as you get further away from the star. Now the inner planets 1b and 1c were detected first. And so those were actually first observed by the Hubble Space Telescope in 2016, and the results were published by DeWitt and collaborators. What they did to observe these planets was wait for the planet to pass in front of the star and block a bit of the star's light. This is what's known as a transit. It's how we actually detect a lot of planets are there in the first place. Now, if you take the light before the transit of just the star, and then during that transit and take one from the other, you'll be left with just the light that's passed through the planet's atmosphere, so that you can see what effect, if any, the planet's atmosphere has had. So if it's got molecules like water or carbon dioxide in there that might steal away certain wavelengths of light. And so this is what DeWitt and collaborators did for the two inner planets first, 1b and 1c, and found that there wasn't much there in the way of atmospheres. The signal that they got was very weak. Now, JWST has also since found the same thing for TRAPPIST-1b and TRAPPIST-1c, but instead of doing this thing where you wait for the planet to transit in front of the star, with the much more sensitive JWST, which is much bigger than the Hubble Space Telescope, it's got much more light collecting power, you can wait instead for the planet to pass behind the star in what's known as the secondary eclipse, because then what you can do is isolate the reflected light from the planet. Before the secondary eclipse, you have starlight and reflected planet light, and then during the eclipse, you only have starlight. Now, if that planet is just bare rock, no atmosphere, you won't get any absorption of the star's light. You'll just get it all reflected back out to you, which means when the planet passes behind the star, you actually lose quite a lot of light, and you end up with a much bigger overall dip in the brightness of the system than if the planet had quite a thick atmosphere. And in 2023, it was both Green and collaborators and Zebra and collaborators that published these JWST results, with TRAPPIST-1b showing no evidence for an atmosphere whatsoever, kind of like Mercury in our own solar system, and TRAPPIST-1c maybe having evidence for a very, very thin atmosphere. But we've always known that those two planets are very close into their star, so there wasn't much hope on them in terms of habitability necessarily. They were the ones that, of the entire system, were most likely to just be bare rock planets. The hopes really have been on those ones that are in the habitable zone or close to it. So the planets D, E, F, and G, which were again looked at with the Hubble Space Telescope by DeWitt and collaborators and published in 2018. Now, with HST versus JWST, you're looking at visible wavelengths of light, your telescope is smaller, so there are fewer questions you can actually ask about the atmosphere. You're much more limited in the data that you can get. You can sort of ask, is there no atmosphere, or is there a very, very rich sort of almost like gas giant atmosphere that we can detect with Hubble that's kind of like, you know, Neptune or Jupiter. And so DeWitt and collaborators found that for TRAPPIST-1, D, E, and F, that they definitely didn't have like thick hydrogen gas giant atmospheres. But for TRAPPIST-1G, they couldn't really rule that out necessarily. Perhaps it's something like Neptune out on the edge of this 7-planet system. So that was interesting. They didn't have no atmosphere, but they also didn't have thick hydrogen atmospheres either. But with JWST, that looks in infrared light, you're sensitive to signatures from molecules like water and carbon dioxide and oxygen. So the hope has always been that with JWST, we'll be able to observe the TRAPPIST-1 planets that are in the sort of Goldilocks zone, that, you know, it's not too hot and not too cold for life, and perhaps gain evidence that says, yes, these have atmospheres that are like the rocky planets that we see in the solar system, and they have what seems to be the conditions that at least would support life as we know it here on Earth. That work is still ongoing, and we will get to that later. But in the meantime, since these observations in 2018 using the Hubble Space Telescope, people started considering, well, how could a system like this form in the first place and come to be? Which brings me to point 2, what we think is happening with planet formation around red dwarfs in general. So like with all planetary systems, we think the star and the planets in orbit around them all formed at roughly the same time from the same giant cloud of gas, mostly hydrogen gas, but with some heavier elements in there, that collapses down under gravity, and then in the densest region in the center, it gets hot enough to start fusion, hydrogen into helium, and the star is born. You then start producing light and heat that starts to push back on all the material around it, separating the star out from the rest of the material in the cloud. Usually that collapse down also initiates a spin as well, and once you've got a ball of something spinning, it flattens out into a disc. Just think about when you take a ball of pizza dough and throw it above your head and set it spinning, it flattens out into that flat pizza shape. So yes, the star will be spinning, but also all that material left over around the star will also start spinning, and therefore that'll flatten out into a disc, and all your planets will form from there. The question has always been though, like, why do we find certain types of planets in certain like distances from their star? So for example, like in the solar system, like why do we find all the rocky planets in the inner solar system, like close to the sun, whereas all the gas giant planets on the outskirts of the solar system further away from the sun? And the thought process is that during that sort of like proto-star, proto-planetary phase, when you've got a lot of radiation coming from that newly born star that's also very energetic, like in the UV and X-ray, then that's going to push out a lot of the lighter molecules, like hydrogen and helium, for example, and push those out through radiation pressure, like out to the outer edges of a planetary system, leaving the heavier molecules that can resist that sort of push from the radiation in towards the center. Now, depending on the type of star you have, you're going to have different radiation environments, especially in this sort of early days of formation of the system, what we call the pre-main sequence star phase. Red dwarfs are particularly problematic in this phase because they're so much smaller and you get a lot more sort of dramatic convection as heat rises and falls inside the much smaller star. Then you get a lot of magnetic fields being set up, which then get all tangled, and you end up with more extreme like X-ray flares that are given off by the star. Those flares bombard newly formed planets with even more energy, taking not just the, you know, the lighter elements like hydrogen, but maybe even some of the slightly heavier elements like oxygen and carbon out from those sort of inner regions of the system as well. And if you start with a planet that's formed with, you know, what is a relatively thin atmosphere in terms of atmospheres, like the Earth, not that thick of an atmosphere when you compare it to, say, Jupiter or Saturn, then those kind of planets will just have their atmospheres completely stripped away. But when we look at other planet systems, we see what's known as hot Jupiters, gas giant planets orbiting close into their stars, which we don't see in the solar system. So we have to then rethink our ideas of, okay, well then what happened in this planet formation stage? And people reckon, okay, maybe these planets did still form further out, where you reckon all of the lighter hydrogen goes, and so you can get these big gas giants forming, but then once the stars settle down and over millions of years, the gas giant planets slowly migrated inwards. But then another type of planet that we see in other planet systems that we don't see in the solar system are like super Earths or sub-Neptunes that are somewhere between like a rocky Earth and a gas giant Neptune. And so those have been really hard for us to explain with our models that are based on what we see in the solar system. But now what people are sort of considering is this hypothesis where a lot of planets maybe do start with big, thick, hydrogen gas giant-like atmospheres, since there is so much hydrogen there in that initial formation stage of the star forming and the planets forming. Then as the star starts to throw off more intense radiation, those planets further in towards the star do lose that big, thick hydrogen atmosphere, what's known as their primary atmosphere. And the big question is there anything left behind afterwards once the hydrogen is lost? Is there a secondary atmosphere there by the time the star has settled down? And this could be the saving grace for red dwarf stars and their planets. We just need to know if it's possible or not. Which brings me to part 3, and this new model from Krissansen-Totton and collaborators. What is it showing for the planets TRAPPIST-1b and 1e? So what they do in this research paper is they model a newly formed planet that's solidifying from liquid magma with all of the heat it's losing. Is it cooled, balanced with the energy it's receiving from the star in terms of the UV, the visible light, and the infrared, and how that affects any atmosphere around it. They model everything and they track the surface temperature and the pressure of any atmosphere and the amount of different molecules left in those atmospheres as well. And they use the measured masses and distances of those two planets as inputs to their model, including, the amount of light they should be receiving from their star, to try and model what could be going on with their atmospheres. And they start first with TRAPPIST-1e. And they say, okay, let's imagine that TRAPPIST-1e formed with something similar to what Earth has now in terms of atmosphere, like not a big gas giant atmosphere. And here's the results of all the things they track in their model. So first of all, in these plots, on the x-axis, you have got time. So you've got around about a few 100 million years passing here. You've also got a dashed vertical line in each plot. That marks the time at which the surface of the planet solidified from magma to solid rock. And there's a few things I want you to focus on here. First of all, the planet still does have an atmosphere after a few 100 million years and once the planet's surface has solidified. You get an atmosphere that's carbon dioxide dominated, which is the green line, with some oxygen and water thrown in there as well, but that still has a fairly high surface temperature. So the good news is that in this model, TRAPPIST-1e, this planet that's in the Goldilocks zone, seems to, after hundreds of millions of years of being bombarded by radiation from its red dwarf star that it orbits, does still have an atmosphere. It's just, there's no guarantee that that atmosphere would necessarily be habitable. The conditions would have to be just right. But it is still good news that it seems to still have an atmosphere after starting with something that's Earth-like. But then what they do in this research study is say, okay, well, what if instead TRAPPIST-1e formed with a thick hydrogen atmosphere that's kind of like a gas giant like Neptune? You can see that in this plot here. So all these plots are the same as what we were looking at before. And if you look at the concentrations of the different molecules in the atmosphere, you can see this huge amount of hydrogen it had in this orange line, at least before the surface of the planet solidifies and becomes rocky. It takes longer to do that. That dashed line is shifted to the right here compared to the other plots. But once it does, a lot of the hydrogen gets lost to space and you're left with an atmosphere of water, carbon dioxide and oxygen dominating. You can also see that the surface temperature drops to become really stable at kind of habitable temperatures as well. So this scenario where you start off with a primary atmosphere that's like a big gas giant atmosphere like Neptune leaves you with a rocky planet that has an atmosphere, a secondary atmosphere that would be habitable to life as we know it. Compare that to what they find for TRAPPIST-1b, which is the planet that orbits much closer into the star. Again, you start with this big, thick, hydrogen-rich atmosphere around it. All of it gets stripped away except for the heaviest of molecules in O2, oxygen, leaving a really thin atmosphere. And yes, okay, you might think oxygen would be good, but at those kind of concentrations, and especially in a very, very thin atmosphere, like that would be suffocating. Plus, all the carbon-containing molecules get lost to space as well, so you don't have any of the ingredients needed for life present on the surface. So it's a really interesting study, one that suggests that TRAPPIST-1b in any scenario wouldn't be left with an atmosphere that could support life. But TRAPPIST-1e, in either scenario, either starting out with a pretty thin, like Earth-like atmosphere could still survive the bombardment of, you know, the radiation from its star and end up with an atmosphere that maybe could support life. And then also if you have, you know, a huge, thick gas giant atmosphere as the scenario that you start off with for TRAPPIST-1e as a primary atmosphere, you're still left with a secondary atmosphere that could possibly, potentially be habitable to life as we know it, which is really promising. And it tells us that we should expect to find something with JWST. That is just all models in theory though, and it's only one model to boot as well. Different models could find different things in the future. And obviously the key thing would actually be finding evidence in observations for TRAPPIST-1e and D and F and G while we're at it as having atmospheres, again, that have those like markers in the atmospheres that the molecules that we know support life here on Earth are present. Which brings me to point 4. When will we finally see JWST results for TRAPPIST-1e published? That really is the big question. Now, NASA makes all of the JWST planned observations for each week public. And once an observation is made, it then gets listed on the public data archive site for all of NASA data. That data is often proprietary, so you know the science team who applied to get that data in the first place and put all that effort into planning the observations actually gets like 6 months to maybe even a year to look at that data first before it's then released publicly. But if we look for TRAPPIST-1 data, we can see there's been so much data taken over the past 3 years, and yet we still haven't heard anything from the science teams that applied for the data. Now, everything I'm going to say from here on in is pure speculation because the astrophysics rumour mill does like to churn. And what I've heard on the grapevine is they got a little bit unlucky with the TRAPPIST-1e observations in that the star flared as they were taking them. So the star got brighter in an unpredictable way, which has made it really difficult picking out, okay, what is the starlight and what is the reflected planet light in what we're seeing. What you've got to remember is that this is the first time that this has ever been done, right? JWST data is still relatively new to everyone in the field. So the science teams will literally just be firefighting problems and challenges as they pop up. And there's no like examples of how this has been done in the past to guide you for what you're supposed to do in this situation. So if we're gonna get some published results that we trust, then this is gonna take a lot of time, right? To get at that robust result. Or it might even be that the observations are not actually useful and you can't get anything out of them, which means that the science team are going to have to put in a new proposal for new observations with JWST, which in itself takes time, and also that whole application process of filtering through all of the applications takes time as well. We just had a whole round of proposals go in this month, which was insanely competitive. It was 9 times oversubscribed. Something that I'm planning to talk about in next week's Night Sky News episode for this month in November. Either way, I don't think we're gonna see published results on TRAPPIST-1 data anytime soon. Maybe we might get data for the planets D and F, which might surprise us. Who knows? Maybe they'll turn out to be the dark horses. But I think what this means is that sadly, the prediction I made in like my roundup video for 2023, I think we are going to get, you know, a paper that claims to have strong evidence for a biosignature in an exoplanet's atmosphere very, very soon. I don't think that prediction is gonna come true in the next, 6 weeks that we've got left of 2024, sadly. But, a girl can dream. Alright, are you gonna actually let me film? Are you gonna let me film? Or are you gonna make a 2-ton noise and be a little menace? I can already tell you're gonna be a menace. And when did you come out from underneath the couch? And why are you now wobbling the tripod of the... Okay, yeah, you just settle there. She's kind of leaning against the tripod, but I don't think she's moving it. She says... Yeah, you settle there, baby girl. Look how cute you look. Let me take a video so everybody can see how cute you look. Hi. Look at she looks so cute. No. That was so cute, but you're not going to be able to stay in here if you keep doing that. Usually that collapse down also initiates a... Gonna get this. I don't know why I'm struggling to do this at once. Speaking and hand gestures at the same time apparently is too much for me on a Friday afternoon at 5:45. I'm done for the week.